attending the third of the Corva webinar series with today's subject, bit projection, seeing to the bit. I am your moderator, Russell Whitney. We ask that you hold all questions to the end of the presentation and utilize the Q&A feature of the Zoom webinar interface. Due to the volume of attendees and the interest of time, we will read questions from this list and answer in order received. Tyler Hines is a product manager with Corva and has 20 years of experience in oil and gas. He has held various roles such as driller, directional driller, and company man across varying regions, including Alaska, North Dakota, Ohio, and Texas. He currently studies computer science, and his interests include reading, research, data analytics, machine learning, and helping people solve problems. And now, ladies and gentlemen, Mr. Tyler Hines.
Great. Thanks for the introduction, Russell. I will share my screen with everybody. All right. Well, I appreciate everybody being here today, attending the webinar to learn a little bit more about the pretty exciting projects that we're working on here at Corva. So I'm going to run through the bit projection app, which is one of the first apps that we're working on in a suite of directional products here at Corva. Okay, so just quick agenda. I'll give a little bit of background on some of the information that you probably need to know going into it, into the app. I'll quickly run through an introduction to the app, kind of show you what it looks like, which will kind of segue us into reviewing each unique section of the app so you can kind of understand the data and how the app functions. We will review the slide and rotary projection logic so that everybody can understand that. And then we'll move into talking about the accuracy logic, how we kind of quantify some of the data points as far as our projection values at each interval versus the actual survey values. And then we'll move into a Q&A. All right, so we will get started. Okay, so the question is why do we need projection to the bit? So an important thing to really understand about this is to understand where the wellbore is being drilled, the rig takes surveys with their MWD tool. Those surveys give us values at surface. Basically, we can plot an XYZ coordinate, which is a survey station, that kind of plots the path of the wellbore as it's being drilled. So normally, when the well is being drilled, we'll have multiple survey stations across the entire wellbore. We'll have survey station 1, for example. We'll have survey station 2. Typically, when the rig is drilling, they'll have difference between these survey stations in most sections of the well is about 95 feet. Sometimes in other sections, it's like 30 feet, but that doesn't really affect anything. So the one thing that's of interest to explain why we need projections is our survey stations are typically about 40 to 60 feet behind where the actual bit is. So if the rig was drilling right now, right here, and they needed to get another standard drill pipe to continue drilling, they would get a survey and then they'd project ahead to the bit. So this distance is kind of an offset distance between the bit and the sensor and the MWD tool. So essentially what's happening here is they're performing a straight line projection here. So we have our multiple survey stations. They've got this new survey just now, and then they project ahead to the bit so that they can understand which direction the bit is moving towards. And these projections typically, when they're done in the field, for the most part, they're straight line projections. So that's an important note. Okay, so the previous industry standard, just to kind of recap, is the rig will drill down, they'll take a survey. When they get that survey, they'll kind of project ahead to the current, they'll approximate where the current bit position is, and this acronym is a projection to bit. So you can see they continue drilling, made another straight line projection. They're kind of trying to approximate where the bit position is by using these projections. And again, they do one projection at every survey station. So this is the way that the industry is currently doing it. The problem with the issue with doing only straight line projections, well, first issue is you usually only get one projection at each survey station. So you project ahead to the bit here. So at this survey station, when I got it, they projected the bit at straight line projection here, but you can actually see the actual path was curved across that same interval, which is also what we're displaying here. So at this survey station, you can see they're projecting a straight line here, the actual wellbore path, because we know that it is never going to drill in a perfectly straight line, is actually kind of along this curved arc. So this margin right here is the error that you get from simply doing just straight line projections. And also, again, these projections are important because as you're drilling your curve sections and you're going to land on trying to land in your target zone, if you're back here and you're making straight line projections and you're in the center of your zone, it might not be so bad. But if you're here and you're projecting straight lines, you might end up down here. You don't really know where your error margins are because you just don't have quite enough data. So how can Corva help us solve these issues? So Corva's solution that we came up with, that we've been working on, is trying to automate a lot of these things, a lot of these calculations, kind of trying to leverage all the inputs that we have already built within the app so that it kind of simplifies everything for the users, or most things for the users. So our bit projection app, instead of just having one projection, which is the current industry standard from the survey station to the bit, we are projecting multiple data points across this entire interval. So as they're drilling this, we are calculating and automating those projection data points every 30 seconds, which essentially ends up giving us 1 to 2 to 3 data points per foot, depending on how fast they're drilling. One of the other things that we can differentiate, and we'll talk about this more a little bit here in a few minutes, is assuming we're rotating, we're going to make these projections in this direction. But if we change operations and now we know we're sliding, which the app automatically picks up, now we know, okay, we're sliding, we're trying to change direction of the wellbore. So now we can kind of adjust on the fly and automatically to kind of change the direction of the wellbore, which is kind of what we talked about before. If the actual survey station came in here, we would kind of have a more representative path of what changed over those two intervals instead of just doing the one straight line projection. Okay, so how does this help? So this empowers users with many other features and enables real-time visuals. So we have some visuals you can see how it's changing across the wellbore, whether it's sliding or rotating. We also calculate automatically at each of our projection intervals, divergences to plan. So you can see how far above, how far below, left and right of the plan you are in real time. So you can see if you're converging or diverging from the plan. We also kind of break down the slide and rotary trends while we're doing this for you. And we calculate some of the divergence and validation accuracies as well. And we'll go into more detail on that here in just a moment. Okay, so we will kind of quickly run through the app, just give you an example of what it looks like. So here's the app, and momentarily I'll go through each section so you guys can actually see what's a little bit more detail. So one thing that's really important, I kind of mentioned it a second ago, was the app is operationally intelligent. And what does that mean? It basically means we have surveys here, but if you look at all the apps, we have all the visuals, we have the wellbore profile, so we have planned and actual paths. The dotted line is planned. But notice the coloring schemes here, and this segregation is we have slide drilling, we also have rotary drilling, and in our wellbore visuals, you can see you're sliding here, or you're rotating here, you're sliding right here, change direction, and you're rotating again. And on this side, you can actually see in this northings and eastings view that they actually were sliding straight left on that slide, which is right here. And you can see out here at this survey station, they were basically 15 foot to the right of the plan. And just on this one projection right here, you can see where they slid and adjusted direction, turning straight left. And now we're projecting at the bit as they're drilling. Now they're only 2 feet left of the plan line. So these are the divergence to plan numbers I was referencing a minute ago. So the visuals are all separated by slide and rotate. The parameters are also separated by slide and rotate, as well as the sliding trend and rotary trend information as well. Another important thing to kind of note, I mean, this is the same whether we're doing it in Corva or whether we're automating or whether you're doing it in the field. We have to know certain values. We have certain dependencies in the app. So for example, we need to know the BHA information so we can approximate motor yields. We also need to know, we need to have the data of the current well plan. So our well path, this is a planned path, is the dotted lines in these visuals. A really important one is our actual surveys. So when a new survey comes in, we need to have that information in a fairly timely manner. And another really important thing is the tool face, the real-time tool face data, so that as we're making our projections for the slides, we can actually point the projection in the correct direction. Okay, so I'll go through quickly each of these sections. I won't go into too much detail. I just wanted to kind of show you each section so you can kind of understand how the app works from top to bottom. I also have a little legend here in the top right-hand side, just kind of highlights the sections that I'm kind of talking about. Okay, so the first section is the survey table. It basically shows projection information for the bit. So this is kind of our pseudo calculated bit projection to that point. And then below that, we have the last survey information. So we show these by default in the table here on top, so you can see the differences between the plan, the last survey, and the projection to the bit, and how you're either converging or diverging, you know, above, below, or left, right. Okay, so the next section, moving down the app, is your two-dimensional wellbore plots. It shows both of these plots are always going to show the current well plan. They're also going to show the actual trajectory paths that we're drilling. So we have two views. We have this view is our side view. This is the top view. The side view actually shows TBD by vertical section. It's as if you're standing at the same level looking at the well from the side. And the top view is if you're looking at the well from straight down. Okay. All right, moving down, we also have a drilling parameter summary section. It just provides a quick reference for data ahead of your previous survey. So in here, in this example, it shows your slide ahead of your current survey station was 26 feet and your rotate ahead is 30 feet. Then you can kind of see the diff pressure, weight on bits, RPM values, tool face values, etc. And these, another thing to note real quick is these values are updating anytime new drilling telemetry data is coming in. Okay, so the lower section of the app, we have the rotary trend and slide trend gauges. I won't go into a whole lot of detail on this at the moment. We'll cover some more details, but basically we have a rotary trend chart. Those values are kind of derived from a different app that we consume in the bit projection app. We can use those values for a couple hundred feet past the previous time we calculated it. But one thing to note that's important is when we're doing these rotary trend projections, the default case is always going to be a straight line projection. So if we don't have more advanced RTA stuff, we'll just use a straight line projection as the default. So quickly to understand the rotary trend chart, we have a rotary trend here. This is the depth where we calculated the rotary trend from. We have build rates, turn rates, calculated DLS change, dogleg change over that interval. And we also calculate a drift direction. So you can see which direction the assembly is drifting in real time. Fairly similar information here on the slide trend chart. We show the depth, build rate, turn rate. We calculate motor yield. We'll go into more details on that in a minute. And then we also calculate an effective tool face. This is the value that we're using to make our projections. Basically, this is the direction we're projecting. So these values, again, are updating in real time on the slide trend, and the rotary trend values will present the depth that we got that value from, or those values from. Okay, so we will quickly go into the rotary drilling projection calculations. Okay, so one thing to note, currently this app is built to run when we have conventional assemblies in the ground. It doesn't currently support rotary steerables, but that's something that's potential for the future, I guess we should say. Again, like I mentioned a minute ago, in rotary drilling, we are making, the default case is always going to be a straight line projection. So kind of like we were talking before, if we don't have a rotary trend value that we calculate internally, the default is the straight line projection. So how does that work? So how does Corva calculate the rotary trend calculation? So basically what we do is we have two survey stations, well, the old survey station, the new survey station. If between these two surveys, we have a 100% rotary, what we can do is we can calculate build and turn rates from that. And this is done in a separate app, which I will show you here in just a second. So instead of just making the straight line projections from the current survey ahead to the bit, we can actually apply this rotary trend analysis data, which has a build rate and a turn rate, to actually kind of project across this curve here, which gives us a better approximation of where the bit actually is instead of just making a straight line projection. Just a quick plug, this is the rotary trend app. This is the app that's actually running in the background on its own cloud thread, calculating build and turn rates. So you can see each of these data points basically represent 100% rotary between two survey stations. And then it shows you the turn rate on the x-axis and the build rate on the y. On the y-axis. Okay, so just another example. The way that this rotary trend analysis works, it's pretty simple, really. But basically, if we have a rotary trend that we calculated between these two survey stations, and it uses, these values, if it's 100% rotary, we'll use it. And then on the next one, between these two intervals, if we have another rotary trend set of values that we can use, we'll use those to make our projections. On the other hand, if the previous was rotary trend, we have those values stored in the back end. But if the previous between these two survey stations was not 100% rotary, then we can actually use the original, the previous one. We do have some constraints built in. We found that some extensive research, we found that anything more than 3 stands or 300 feet, these rotary trend values don't really apply. So anything after that, we'll just use straight line projections. And yeah, okay, so key takeaways for the rotary drilling projections is the base case is always straight line projection to the bit. Corva improves rotary projections using RTA app data, which kind of gives us a better approximation of where the bit is. Okay, so now we'll go through the projection calculations. Okay, so moving on. Okay, so we use the minimum curvature method, which is kind of an industry standard nowadays. It's not always done by hand because it's kind of time consuming, and you'll see that in a second. But basically, if we have two survey stations, survey station 1, survey station current, the minimum curvature method assumes that the wall path fits on the surface of a sphere with the radius of r. Again, this information is Fundamentals of Drilling Engineering by Mitchell and Miska. It's well-known set of calculations. Here we have current survey station XYZ 2, sub 2, and then we have XYZ 1, which is our previous survey. So a bunch of fancy calculations that we do have been pretty extensively tested, such as the ratio factors and beta we have to solve for. So the ratio factor is the course length over beta. So then we have to solve for beta. So beta is course length over the radius, solve for the radius. And we get some of that information from the bit tangency method, which we'll talk about just a second. Okay, so the bit tangency method, we built out and tested quite a few different methods. I think we did the 3-point of contact method, which we found wasn't super efficient. Then we tested this bit tangency method, and basically it allows us to kind of define some variables of what is currently in the hole, so we can have a really good approximation of what our motor yield is. So we have upper point of contact, and then we have an L2 variable, an L1 variable. Of course, we have to know what our bit to bend is. That's basically this value. And it's kind of like a fulcrum. So as we know these points, it's kind of a physics-based calculation, but as we know these points, as you apply weight on bit in this direction, it kind of moves the bit, up or down more in one direction or the other. So the input variables, obviously, for this bit tangency method are motor length, bit to bend distance, upper point of contact, which we'll cover more here in just a second. We have to have ODs, bit diameter, bend angles, etc. Okay, so how do we define upper point of contact? So within Corva's environment, we have several different collections that we have access to easily. So when we get new BHAs put in for the current run, we consume those values in Corva, and then we can just go get those values and plug those into our bit tangency method to approximate motor yield. So our upper point of contact on this BHA with a stabilizer would be this top stabilizer here, which is above your motor. We also already have motor bend information. So therefore we can calculate our L1 and L2 values. And then, excuse me, on a BHA without a stabilizer, we do the same thing. We look at upper point of contact, which in this case will be the top of the motor, calculate our L1, L2 values, plug those into our bit tangency method, and then we can get a pretty decent approximation of motor yield. Again, this is just kind of a quick overview of the app, but some of the dependencies of this app are going to be, to make the good motor yield approximations are motor bend angles, the motor OD, the length of the motor, the bit to bend information, any stabilizers that we have in the motor, the lengths of them, and the gauges of them. Another thing, because there is dependencies on knowing this information, we have some error messages within the app that basically can show us like, hey, the calculations are not quite right. Here's the error. Basically just shows you that you're missing bit to bend information, which is an input to the bit tangency method calculations. So that way we can get that fixed quickly. And the users also, it enables the users to actually know what is missing as far as BHA information. Okay, so key takeaways from the slide drilling projection calculations. The default mode, as the industry standard, is the minimum curvature method. So to solve that in real time, we have to use motor yield. We have to get motor yield, inclination, and azimuth. And again, motor yield is estimated using the bit tangency method. And then inclination and azimuth angles are derived from live toolface data streams. Okay, so now we'll talk about the slide trend calculations and kind of walk through that. Okay, so this is our slide trend chart. Again, it's in the lower section of the app. So how do we do these calculations, and how is that updating in real time? So basically the way it works is we have our XYZs. While we're drilling, we have these rotary projections here. So what we'll do is we'll continually monitor in real time the drilling operation, so we know if you're sliding or if you're rotating. We see that the operation has changed, so what we do is we use this first point of our sliding segment as the start of that segment. Then as you continue to slide, we'll be making projections and updating our projection values in the slide trend chart as the slide progresses. So an important thing to note is we always use the first data point and the last data point to calculate our build and turn rates for the slide trends. So as you can see, moving along, they get a new data point. We calculate the distances between this, and that's how we're updating our build rates and turn rates in that slide projection. So the other important thing to note here is, as you know, the slide progresses, it gets a little bit longer. You can see if we're calculating your build rate. So build rate is calculated by delta inclination over course length, and then turn rate is delta inclination over azimuth. As you can also see, the denominator in both of these equations is course length. So what happens is when you have a really short course length, the values are not quite as accurate. But as your slide starts to progress, those build and turn rates will converge to what they actually should be. And it doesn't take very long to do. We just wanted to be transparent on that. Okay, so slide trend key takeaways. We have a real-time output of build and turn rates while you're sliding that are updating every time we get new projection data points. And again, as the slide length increases, the build and turn rates will converge to actual, and then we have the build and turn rate calculations listed so you can see those and understand why, if you're only 1 foot into your slide, some of these values might be a little bit high, but as you progress, they will normalize. Okay, so another important thing that we need to talk about for doing these bit projections is how do we, Corva has all the input data that you guys already have. We're making these projections in real time. How do we validate how accurate these projections are? And I think this is an important thing to understand. So we have in the center of the app, we have this projection divergence at last survey. And I'll go through that here in just some more details in just a moment. So these values are calculated every time we get a new survey. So previously I showed you all the data points between these two survey stations and the bit. And then when we get a new survey, we can calculate these values. And also a really important thing is everything is calculated against the last known survey position. So that is our ground truth for comparison for what we're doing. One important thing to note, and you'll see this here in a second, some more info, is we calculate projection distance and divergence to survey. And these distances are in reference to the last survey. That way we can kind of quantify how close our projections were versus the actual survey station. So there's a little graphic to kind of show that visually, so it makes a little bit more sense. So we'll just say that we have a survey station here at 10,000 foot. Obviously, we know our bit to sensor distance is offset by 40 to 60 feet. So in this instance, we actually used 50 foot. So we got our survey, the bit's 50 foot ahead. We'll continue drilling, getting our new data points. They're updating every 30 seconds. Okay, so now we're roughly about 90 feet ahead. That's an average drilling stand length. So then what happens is we're collecting all this data on the back end. We know where the bit is. We know where the last survey was. What we'll do is when the rig drills that stand down, makes a connection, and they get a new survey, we will go in as soon as we see that survey, and we will calculate algorithmically the closest to projection data points to the survey. Then what we'll do is once we find those 2 points, and this is done automatically, by the way, we'll calculate the minimum curvature method between those two, and then we will interpolate a new survey point that's at the exact same depth as the survey. So basically we intersect that here, and then we get a new data point, which is again calculated at the same exact depth as in the survey. And then what we're going to do is once we have that point interpolated, basically you're doing a little bit of the Euclidean distance is what we're calculating, but it's basically the change in your horizontal and your vertical section change, and then basically calculating this hypotenuse of that. So the distance between these two surveys, or the divergence between the actual survey and our projection, is the Euclidean distance. It's not a measured depth. It's the hypotenuse of your triangle, if you will. And again, that's 1.2 feet difference between those two stations. So the other thing I pointed out a moment ago was the projection distance at last survey. So that projection distance is the distance between the previous survey and the most recent survey. So that course length would be, 95 feet if surveys are coming in on a, in a timely manner. So projection distance at last survey. Again, that's what we're displaying here. And that 1.27 feet, which is the hypotenuse of your triangle, Euclidean distance. We also show your projection distance here, and your projection to survey distance. Just another note, we are actually kind of working on breaking this out just a little bit more in a future update, so you can actually see the change in all three. You can see your hypotenuse length, your C value, and your A and B value, so you're changing horizontal and vertical displacement. Okay, so moving right along, this is an example of a well that we drilled that just shows some of the divergences, distance to survey. So you can see in the vertical section here, most of our projections were really, really good, really accurate. A lot of them are right close to zero, so almost the exact place where the surveys were. But on average, I'd say they're less than a foot of error margin in the vertical. Same in the lateral here, it's less than 2 feet. And then you can see in the curve, there's a little bit more error, but this is one of the highest build and turn sections of the well, which it's not uncommon to see that error. So a couple important things. Again, we talked about getting surveys in. So as we're drilling, it's the same for the directional drillers on location. If they don't have the most recent survey and they're projecting from 2 surveys or 3 surveys back, their projections are going to be just as bad, as you would expect. So timely input of surveys is really important. It's key to making sure that you keep, less of these and more of these lower values. So on average, this app, like I said, runs every 30 seconds. We're getting 1, 2, 3 data points per foot. So we're generating anywhere from 20,000 to 30,000 data points per well with all of this information. Again, on average, error margins are less than 2 feet. Sometimes they're even more accurate, as you can see in this example. And we've done several pretty large case studies for several large clients of ours to kind of show the differences between DD's projections and Corva's projections and how much more data we can show. So we've done tons of research to kind of validate all of this information. So a couple of important things to note here on data quality. So in here, this is kind of an example, kind of an edge case, an extreme case for this survey data. So this rig is drilling the curve, and you look down here and you see projection divergence at last survey is 49 feet. Well, what does that mean? Well, you can see here when you hover over this that it shows 221 feet. So that basically means between this survey and the previous survey, which is probably up here somewhere, that course length is 200 feet. So the divergence to survey, because that course length was so long, was really high. So we might have been projecting up here because this course length was so long. And I mean, as anybody who's been in the field knows, the longer that course length, the higher your error margins are going to be. So the survey could be, anywhere in this interval. So again, that's why it's important to make sure your surveys are getting put into the system in a timely manner. So this is an opposite case just to show real quick for a rig that was doing a really good job. Surveys are in right on time. They're making their projections. You can see your divergences. Important note here is, even though we're in the curve, our projection is only 2 feet off. But here you can see the projection distance was 34 feet. So that previous survey came in here. So when we got back to this to make our comparison, we were only 2 feet different. So again, key to make sure surveys are getting put into the system in a timely manner. So another really important thing, especially when you're sliding, is you have to have tool face data, good tool face data. So in this example, let me just start it from the beginning. So in this example, they're drilling the curve section here. They're on bottom drilling. We're getting tool face values, gravity tool face, magnetic tool face. So we have some rotation sections, some slide sections. And at the top of the curve here, you can see the green slide projections are the blue is the survey. So here's your slide projections. Here's your error margin. This is the value we're projecting, the divergence. And again, a little bit of error margin. Here's your divergence. And then you can see as the curve progresses, our projections are starting to line up. They're starting to come right back around with almost exactly where the survey stations actually were. So very key that we have good tool face data coming into the app. So the opposite case, if we don't have tool face data, when we're going to make these projections, notice here they're just one value. So basically it's 90 right. So this is in the vertical section of the well. And you can see the rotary projections and the slide projections are going off to the right. When you follow these blue dots, they kind of go to the left, down and to the left. Well, why are these shooting straight to the right? Well, when we're making our projections and the direction, that direction is derived from these magnetic and gravity tool face values. So if we don't have those values, we can't give you an approximate estimation. And another thing to note as well is, if we are making these projections that look kind of silly like that, you will see those high projection distance ranges, and you also see the divergence to survey values will be really high as well. So that's one way you can kind of identify issues like this. And I think that is all that I have. And we'll move to Q&A.
Thank you, Tyler. We now invite questions through the Q&A feature in the Zoom webinar interface. Once again, I understand that there may have been difficulty hearing me. We invite questions now through the Zoom webinar interface.
Okay, can you still hear me, Russell?
Yes, sir.
Okay, so some of the questions we have here so far. First one is, do you use continuous inclination or azimuth to make projections? And the answer to that is no. The current version of the algorithm only uses live rotary trend analysis data from the rotary trend app to perform rotary drilling projections. The motor yield is derived from the bit tangency method, plus a live feed from the tool face data. Okay, moving along. Why didn't we use the 3-point of contact method to estimate the motor yield? Okay, so the answer to that is, since we were projecting in real time, got another question that just came in. Since we were projecting in real time, we need estimates of the motor yield to calculate the projection arc of the minimum curvature method. And we are aware of the widely known 3-point of contact method that provides a rough estimation of the DLS for a given VHA geometry, but we're looking for a better estimate, which is why we kind of moved towards and tested the bit tangency method, because it actually provided us with much better results that you can actually see in the data.
Tyler, one question from the audience. Can the motor output input be overridden with local knowledge?
That's a good question. So currently, no, it can't.
Very good. If available, can app bit inclination be incorporated into the app and any projections?
Currently, that feature is not supported, but we have talked about it. We have looked at a few different scenarios, but currently, no, it does not.
Can I safely take a survey every second or third stand to save some time in the tangent section? And how would the accuracy, or would this affect the accuracy of the surveys and the projections?
That's a really good question. So again, we kind of talked about one of the things that we really focused on when we were designing this app is transparency. So there is sections of the well where we've seen, we have 300 feet, 400 feet between the previous survey station and the bit. And our accuracies are still really, really high. So if you have minimal build and turn sections across these intervals, like for example, in the vertical section, yes, you could have 300 feet, 400 feet potentially between those and still have a really high accuracy, but you'd have to kind of monitor that. Where you run into problems is if you're doing, for example, like a nudge or a kickback, or you start drilling the curve, or you're in the lateral and you're changing directions, that's when those longer course lengths will basically derive a higher error divergence.
Sorry, continuing on. Does the app take into account OD of the motor to hole size relationship for predicting build rate?
I don't believe that it currently does. No, it takes into account in the bit tangency method the OD of the motor and some of the other specific information that we added in there, but it does not look at the relationship between the hole size and the OD of the motor.
Would it be fair to say that some of that relationship is naturally taken into account with monitoring the actual bottom hole assembly trends, as stated in the rotary trend analysis and the motor output collections and calculations in Corva's system?
Yeah, I guess inherently, implicitly, it could be, yeah.
Tyler, another question from our audience. What is your plan for predicting and recommending ahead of the bid in order to reach a landing point? So going beyond the bid and achieving a certain target or hitting a certain directional target.
That is a fantastic question. So to give a little bit of background on this, so we are currently working on other directional products as well. So this bit projection app really kind of sets the stage for the back end engineering and algorithms to do that. So essentially, to answer your question, yes, we have that in our sites. It's currently not an implementation, the current MVP for bit projection, but it's not too far out, too far of a reach to extrapolate that data. I mean, we already know build-in turn rates for whether you're sliding, whether you're rotating. So technically, yes, we could take those numbers, extrapolate them out 100 feet, 200 feet, or maybe even to the bottom of the curve and do that. But I don't know if that will be in the bit projection app, but it may be in another app coming soon, we'll say. Any other questions? Any other thoughts, Russell?
Oh, my apologies. So I think it's fair to say from that comment, Tyler, that bit projection is just the start of our, as well as rotary tendency analysis or rotary trend analysis of our directional product offering. And the work that we put into making this app a success lays the groundwork for a future and expanded directional product offering for our clients to help them in such as an example of hitting directional targets.
Yes, exactly. That's exactly. We are, and just as an update, I mean, we are currently working on some other pretty exciting stuff. Without giving too much details, but yeah, I mean, if we can accurately project rotary trends and slide trends across an interval, the next logical step seems to be, well, if we can do that and we can calculate the trajectory path that needs to be drilled, why could we not extrapolate a little bit further and actually tell you how to get from point A to point B and monitor you in real time as that progresses? So that's some future stuff we're working towards.
One user has asked, how often will the field see updates with this app? Such as if the directional driller is using Corva in real time.
Mm-hmm. Yeah, so again, we have all of the inputs, hopefully, if they're making the projection. So we have the motor information, and we have the telemetry information. So this app actually, on the back end, is doing a lot of the heavy lifting using some cloud computing, Lambda functions, some fancy, gibberish, but basically it runs automatically every 30 seconds while they're on bottom drilling. So the difference between a projection, it might be, half a foot, it might be 1 foot, it could be 3 points in 1 foot. So the app is continually updating with the most recent information that it has every 30 seconds.
Are there any further questions from the audience? Well, Tyler, thank you for an excellent presentation. This concludes the Corva webinar. Please join us next week as Michael Lauder presents Achieving Continuous Improvement through Metrics in Corva. We thank you all for attending and look forward to seeing you next week.
Thank you, Russell.